Potential energy can be due to many sources. So we have historically something called elastic potential energy, which has to do with springs. Then we have electric potential energy, which is due to a charge in an electric field. And we have gravitational potential energy. Gravitational potential energy will be the focus of our conversations in this class. By definition, it's m times g times h, where h is a height. It could also be m times g times y, or more appropriately, m times g times delta y, a displacement along the y-axis or along the vertical. Okay, if we look at the units, you'll notice that m is a kilogram, gravity is a meter per second squared, displacement is a meter. You'll also notice that a kilogram meter per second squared is a Newton. And a Newton meter, as was discussed earlier, is a joule. So the unit for potential energy is going to be a joule. So here we have an auto shop that's raising a 1,000 kilogram car by 2 meters off the ground. So the ground is going to be 0. Okay, anything above that is going to be a change in the height. So we have the potential energy is going to be the mass of the vehicle times gravity times the displacement, the delta y, right? The vertical height. A firefighter is on a ladder that's 10 meters above the ground. Again, the ground is going to be 0. Okay. Now, when the firefighter descends to 6 meters, so they started at the top at 10 and they lower themselves to 6 meters above the ground. Okay, the potential energy changed, right? Now, by how much? Well, let's see. So the potential energy, we're going to use m times g times delta y, because the delta y is changing. So we have the 50 kilogram firefighter, 9.8 meters per second squared for the gravity. And then we have the 10 meters minus the 6 meters, which ends up giving you 4 meters. Putting this onto the calculator, you get 1960 joules. A stout woman of mass 60 kilograms scales a 40-meter tall rock face. Again, we're going to relative to the ground, meaning that's your 0. Okay, that's your 0. So what is her potential energy? Her gravitational potential energy is going to be the mass times gravity times the 40 meters. For part B, if she were to jump off of the cliff, right, 40-meter height, since the height is relative to the ground, as the height is getting less, the potential energy becomes less as well, right? Potential energy is m times g times the height, or the y. So as this number, everything is the same. Her mass is not changing. The gravity is not changing. We're going to assume that, okay? But the height, as she's falling through the air, that height, that gap, that delta y between her and the ground is becoming less and less. So as this becomes less, the potential energy becomes less until you get to the ground where the height is 0 and the potential energy will then become 0, which answers part C. What is the gravitational potential energy of the large pink air-filled cushion lying on the ground? The fact that it's on the ground, the height is 0 meters, makes the whole potential energy 0 joules. So if the ground is what you're relating everything to, and an object is on the ground, then the potential energy is 0. Now the question becomes, what happens to all this potential energy? Where does it go? What does it become? For your summary, what affects potential energy, and does potential energy only affect the y-axis? Explain.
Goodbye.